This is the second video on determinants, so I'm going to pick up exactly where I left off, where last time we got the determinant of this matrix by going across the first row. I'm going to go again and go down the first column. So first we're calculating the minors here for the first column. So the first one here, M11, right, this is the minor for 3 here, that's in the first row, first column. So to get the appropriate minor, we delete the first row and the first column, and we're left with the determinant of -4, 2, -1, 1, which is equal to -4 times 1 minus -1 times 2 is equal to -4 plus 2 is equal to -2. Next, M21, that's the minor associated with this 6 here in position 2, 1. Second row, first column, 2, 1. So I delete that column and I delete that row. And so the minor here is 4, 5, minus 1, 1, the determinant of that. So that's equal to 4 times 1 minus -1 times 5 is equal to 4 plus 5 is equal to 9. Finally, this 2 here in position 3, 1, third row, first column. Delete those. We have 4, 5 minus 4, 2 equals the determinant of that, 4 times 2 minus -4 times 5. That's equal to 8 times 20. 8 plus 20. 28. So now that we have all those are all the minors. The determinant expanded along the first column is given by each of these numbers here in those positions, that 3, that 6 and that 2, multiplied by the appropriate cofactor. Remember that the cofactor is the minor multiplied by the appropriate sign. So remember our signs, they look like plus, minus, like this. Well, ours is only a 3 by 3 actually, so for the moment it looks like this. Those are the signs for the cofactors. So the first one here for this 3 is a plus. So I'm going to say the determinant of A is equal to 3 times the appropriate minor and positive. So we'll say it's plus, right? This plus up here. Plus 3 times -2. That -2 from here. Next, for that 6 in position 2, 1, the sign of the cofactor is minus. So it's going to be -6 times the appropriate minor, which is 9. Finally, for that 2, the sign is positive. So it's going to be plus 2 times 28. That is equal to -6 minus 54 plus 56 is equal to -60 plus 56 is equal to -4. So that's the same answer. So it doesn't matter if you go across the first row or down the first column or the second column or the third column or any way you want, as long as you get the signs right in your for your cofactors. So as long as you get this right, you can pick whichever row or column you want, and in fact you should probably just pick the easiest one. So if there are lots of zeros or ones in a particular row or column, that might make things a lot easier. Now I'm going to do part D here to give you an example of a 4x4 matrix. Look at the first row here and you'll see that it's mostly zeros. Now I could do the last column either, but that's mostly zeros too, but for now I'll do the first row. So first we have 2. Delete that row and column. So it's 2 times the appropriate minor here, which is the determinant of minus 3, 0, 0, 3, 4, 0, 3, 2, 1. And the sign is positive because it's in the first position. Element 1, 1. Then we add on, we go to the next one here, 0. So that's going to be 0. And the next one is 0. So another 0. And it doesn't matter what the cofactors or minors are here, because you're going to multiply them by 0, so you're going to get 0 anyway. And that last one also 0. So what we have is just 2 times the determinant of this matrix. And this is another easy one to calculate. This time I'm going to use the third column because it's 0, 0, 1. So that makes things quite easy. So that's equal to 2 times, I'll leave that 2 at the front, our first 2 elements are 0, going down. If I'm going down here, so I get 0 plus 0 plus 1 times the determinant of, I delete that row and that, and I get minus 3, 0, 3, 4. That determinant. Finish my brackets. So finally, I have 2, all those zeros are gone, times, that 1 is just 1, so finally I have minus 3 times 4 plus 0 times 3. And that's just equal to 2 times minus 12 is equal to minus 24. And that's our determinant. So that's an example of 4x4. So now a few properties of the determinant. So the first one here, the determinant of the identity matrix is equal to 1. And that applies for any size of matrix. That should be fairly easy to check yourself. You can imagine, no matter how big it was, your first element is going to be 1. We'll delete that row and column, and you'll just have another thing the same in here. And then the rest will all be zeros, so your determinant is going to be 1 times the determinant of the blue part, but that blue part is also going to be the same thing with another 1, and you're just going to keep going inside there, and the cofactors are all going to be positive because it's always going to be in position 1, 1, and you're just going to keep multiplying by 1 every level you go down. So the determinant of an identity matrix of any size is always equal to 1. Next, the term singular matrix is just a term for a matrix where the determinant is equal to 0. It's called a singular matrix. That becomes relevant later on when we talk about solving systems of equations. Next, this one isn't obvious, but just believe it for the moment. If a matrix has any 2 rows the same, or any 2 columns the same, the determinant will turn out to be 0. You'll see why that is as we go on. Next, what does multiplying a row or a column of the matrix by a scalar, by some number, do to the determinant? Well, it's the same as multiplying the determinant by the same number. So there's 3 examples here of that. So, like if you multiply everything in the first row by the same number, lambda. This, by the way, is lambda. It's just a Greek letter used sometimes instead of using x or y or something. It often comes up in the context of matrices, so that's why it's here. That's just a convention to use this weird Greek letter instead of one that you might be used to, but you might as well get used to it now. So, multiplying, say, the first row, every element in the first row by lambda, it changes the determinant by just multiplying it also by the same number lambda. So there's a note here that this is very different to scalar multiplication. And it is, because if you remember, if I just multiply some number lambda by a matrix, that gives me lambda times A, lambda B, lambda C, lambda D. So that's scalar multiplication, where you multiply a matrix by a number, and the result is that every element of the matrix gets multiplied that number. Here I'm talking about a determinant. So lambda times the determinant of that would be the same as the determinant of the matrix that had lambda multiplied across one row. So don't confuse those two things. The top here is a matrix, and the second line here is the determinant of a matrix. So if you multiply one row of a matrix or one column of a matrix by a scalar, a number, that multiplies the determinant by that same number. Next, if you switch 2 rows or columns of a matrix, what happens to the determinant is that you change the sign. So the example here, they've swapped the first row with the second row, and they say it's minus the determinant of the original matrix, and then swapping the first column with the second column also changes the sign of the original determinant. So if you swap rows or columns, you change the sign. If you multiply a row or column by a scalar, then you multiply the determinant by that same number. Next, the product rule. So this one here just says that the product of 2 determinants is the same as the determinant of the product. So it doesn't matter whether you multiply the matrices and then take the determinant of the product, or whether you get the determinant of your 2 matrices first and then multiply those determinants together. Now the addition rule. So if you look here, you have 2 matrices on the right that are the same down here, but they're different on the first row. What the addition rule is saying is that the sum of the determinants of those 2 matrices that are different only in the first row is equal to the determinant of this matrix, but with the first row being the sum of the first rows of the other 2. So you could also think of this as you're after breaking up this determinant on the left into the 2 determinants on the right. So you've said that this first row is equal to a sum of 2 rows, and you've split it up. So for a quick example, let's say that I wanted the determinant of this matrix. I could break that up if I wanted to and say that is equal to the determinant of this matrix. You see I've taken one off from the top right, plus this matrix. Maybe if I already knew what this determinant was, and then I wanted to find the determinant of this matrix, then I could make it easier for myself by breaking it up like this, and I'd have an easy determinant there to find with that one on the right. and I could just add those two together then to get the determinant that I want. The determinant of the transpose. So A and A transpose have the same determinant. Simple enough. Now, if a matrix has a row or column that consists of zeros, then the determinant is equal to 0. To check that that's true, just imagine a matrix with a 0 row. And we want to calculate the determinant. Well, we can just pick the row that's all zeros. And then every cofactor will be multiplied by 0 and we'll get 0 in the end. And the same applies to having one column all zeros. Finally, we get to adding multiples of rows or columns. This is a really, really important one, and we're going to do this a lot. The value of a determinant does not change if a multiple of one row or column is added or subtracted to another row or column. So we can take one row and add some multiple of that row onto another row, and the determinant will stay the same. And this turns out to be very, very useful. So the notation that we use to say that we're doing this is written down here. So what this basically says is that row j, so that's the, if j was 2, that means the second row down. So row j is being replaced by lambda times row I plus row j. So that means I'm taking row j and I'm adding on lambda, which is just some number, times row I, which is some other row, and I'm adding that onto row j. So there's an example here. So the way we're going to approach this one, the solution that's given here, is that instead of expanding the determinant along some row, I'm going to go through a process of swapping rows and adding multiples of one row to another row, to make a series of moves that either change the sign of the determinant, and we keep track of that, or keep the determinant the same. And at the end of it, we end up with a matrix that's much easier to calculate the determinant for. So before we start, take a look here at the matrix that we're going for. And you can see that with that 1 and all these zeros down here, the next move where you expand the determinant down the first column is very simple, because you just get 1 times the determinant of that minor. So that's what we're going for, is a 1 and a bunch of zeros in the first column. So, back to the start. The first move that's made here is to swap row 1 with row 4. Because row 4 already has a 1 in it. So now we get our 1 here in the top left. And so in doing that swap, we change the sign of the determinant. So the determinant of that original matrix is equal to minus the determinant of the matrix with those swapped rows. The next step is to get this 0 here in this position. And the way we get that, if we go back here, we see that it's a 4 here and a 1 above it. So if I take away 4 times the first row from the second row, or row 1 times minus 4 plus row 2, and put that into the second row instead, I'm going to get a 0. So that's 4 minus 4 times 1 gives me my 0. In the next position here, it's going to be 5 minus 4 times 1, which is 1. Here then we have 1 minus 4 times 2. So minus 4 times 2 is minus 8. So 1 minus 8 is minus 7. And then in this last position we have 1 minus 4 times 4. So that's 1 minus 16 is minus 15. So that's how we got that row there. Next, I'm going to get a 0 here. And I do that, if I go back and look, the first row just has a 1, and the third row also has a 1 in that position. So if I just take the third row and I take away 1 times the first row, I'll get my 0. So it's the first row times minus 1 plus the third row is what's going in there to the third row. So it's like I'm taking row 3, I'm replacing it with minus 1 times row 1 plus row 3. So let's go through the rest of that row. So for here I have 1 minus 1 gives me 0. For here I have 4 minus 2 gives me 2, and I have 2 minus 4 gives me minus 2. Finally I go for my 0 here, and to get that, if I look back, that's a 5 in that first column last row, and it's still a 1 on top. So I'm going to take away 5 times the first row from the fourth row. So that gives me a 0 there. And for the rest of the row, this position we have 4 minus 5 times 1 is minus 1. We have 1 minus 5 times 2 gives me minus 9. And I have 1 minus 5 times 4. 5 times 4 is 20, so I get minus 19. So now we have this matrix with 1, 0, 0, 0 down the first column. We expand the determinant around that first column, and we get 1, which is here, times the determinant of that minor. So then we do the same thing to this 3 by 3 matrix. We look, we see we have 1, 0, minus 1. So we actually already have a 1 and a 0. So we just want to turn this minus 1 into a 0. So to do that, we just add on the first row to the third row. So minus 1 plus 1 gives me 0. Minus 9 plus minus 7 is just minus 9 minus 7 gives me minus 16. Minus 19 plus minus 15 is minus 19 minus 15 is minus 34. So now we go again. We have another matrix which is 1, 0, 0 down the first column. So that's going to be 1. That minus is going to stay with us. It's going to be minus 1. The 1 isn't written here. Times the determinant of this 2 by 2 matrix. And getting the determinant of a 2 by 2 matrix is easy. The first step that's done here is actually to change the sign of that last row. So it's minus 16 minus 34. So what's done here is that this row has been multiplied by minus 1 to give 16 and 34. And if you go back to the properties of determinant, you might remember this one, multiple of a row by a scalar. So you can imagine in this case the scalar that we're looking at is minus 1. So what I've written here is like that rule in reverse, but for a 2 by 2 matrix and using the second row. So in this case, it's like instead of lambda, right, we have, that out, it's like we have minus 1. That's what's being done down here in this step, taking this minus 16 minus 34 and bringing that minus outside here. So now we've reduced the problem to the determinant of a 2 by 2 matrix. And that's easily done and gives us our final answer of 100. So that's an alternative way of calculating the determinant of the matrix by making a series of moves where we add multiples of rows to other rows and swap rows around in order to give us easier determinants to calculate. That's it for the moment. Have a go at some of the problems on the next page and see how you get on.